Now I'm going to give the definition of gamma convergence. So, and I will give you, of course, it's very general definition for arbitrary, in fact, metric topological space and with arbitrary topology, but I will give this definition already adapted a little bit to our framework, so I will consider functional defined on R2, L2 over RD or some domain. So we consider the space L2 of Q. In particular, Q might be the whole domain. And some topology on this on this Hilbert space, which might be strong topology, norm topology, or weak topology, or
operators of this space. Topology.
No, of functions on this on L2 itself. There is weak topology, convergence of weak topology of weak convergence, of strong convergence, and also I will use the following topology: weak topology, the topology of convergence, which is weak convergence intersect with local strong convergence. You will see why. Topology of weak convergence. Convergence is like this. We assume that sequence converge weakly, and on any bounded set, it converges strongly. We can introduce easily topology which corresponds to this convergence. I don't have much time, so I don't want to. This is standard. So we will use one of these topologies. So we assume that there is a family f epsilon functionals in L2 of RD with values in R plus infinity. So the value plus infinity is not forbidden. And we denote the corresponding topology by T.
What is the function
of U and U from L2 of RD? For example, this one. That's the map from L2 to numbers. Functional.
Linear?
No. Absolutely general function. It need not be continuous. Very generic functional, but with so far only this is required. Yes. No continuity.
No convexity.
No convexity.
Yes, it's convex, but
yeah.
Not generally doesn't require.
Topology in this space of Q. In particular, Q might be RD. Sorry, we decided to use this. To cover both Dirichlet problem and the problem in the whole space. Then we say definition. We say that f epsilon gamma converges as epsilon goes to 0 to the functional limit functional f0 defined on the same space and with the same property if the following two properties are satisfied. Gamma converge, yeah, it's written. If
with this dash, it looks like F again.
if the following two properties are satisfied. The first one, for any U epsilon that converge to U with respect or in topology T, we have lim inf f epsilon of u epsilon is greater or equal than f0 of u. Lim inf. It would be low semi-continuity if here and here we have the same functional, but since it changed, it's some kind of. And one of the reasons why gamma convergence is very helpful, the gamma convergence results are very helpful in homogenization theory of homogenization theory for equations is there is the following theorem. If f epsilon is, yes, gamma converge as epsilon goes to 0 to f0 in topology T, and if the sublevel sets are compact in topology T, and if u f epsilon of u less or equal than some constant are compact, are T compact, for, yeah, that's the set U such that for any epsilon smaller than some, okay, epsilon below some threshold. Of course, it's, we don't care about large number of epsilon.
Uniform, right?
Uniform, yeah, that's important.
So you can write set of U such that F and epsilon
Yeah.
less than epsilon naught, right?
Yes, epsilon less. Yes. Then the minimum of u epsilon, fortunately I will have to clean this part. Then minimum of f epsilon converge to the minimum f0, and the argmin of f epsilon converge to argmin of f0. If there are several, then we take arbitrary sequence, and it will converge to one of the minimizer of f0. So there's the fact that the minimizer might be non-unique, it's not a problem. And arg min f epsilon converge in topology T, in the same topology, to arg min f0 in T.
So it doesn't have to be L2, right? It's any kind of linear topological vector space.
Not even linear. We consider any functional on any, in fact, metric space, and even topological space. And if this condition satisfied, and
you probably need to deal with functions. Instead of L2, you can use an epsilon Hilbert space possibly.
yes. Yes, okay, now it generalized to this notion of gamma convergence finally was generalized to very general framework. Well, so you see from this, it follows that in our case, it's sufficient to show gamma convergence and compactness. And then since our solutions are minimizer of our functional E epsilon, in our case, of course, F epsilon will be replaced with E epsilon, our energy, and the minimizer of our E epsilon are our solution U epsilon. And they will converge to the minimizer of the limit problem, limit functional. So our goal is to find the limit functional, to prove gamma convergence, and to show this compactness. And for this, we have just 20 minutes. Minimizer if it exists. For this, we know that it exists. For our model, yeah. If we replace f epsilon with our e epsilon, then we know that the minimizer exists, and it is unique. Yeah. If minimizer doesn't exist, then it even works for minimizer sequence. But
the convergence is along the whole sequence or up to subsequence?
Well, I would not take the risk to take that it's always for the whole sequence, but in good examples, it's for the whole sequence. For instance, in our case, it will be for the whole sequence. As usually, if it's not for the whole sequence, if there are several minimizers, then of course it depends. It's for subsequence only. But I think if the minimizer of f0 is unique, then it's for whole sequence. So I think the question is only the uniqueness of the minimizer for the limit problem. Yeah, I'm pretty sure that it's the case. So now I clean this, and I formulate our results. So first, theorem. In fact, that's the main theorem in our framework. The E epsilon. Let's start with the Dirichlet problem. For Dirichlet problem, our topology T is just strong topology, usual norm topology of L2 of G, of Q. Standard topology of norm convergence. Epsilon, gamma converge, as epsilon goes to 0, T is already specified, to the functional E0, which is the quadratic form on the gradient of U with some positive definite matrix theta. If U is from H1, 0 of Q.
Also minus 2 times.
Yeah. Thank you. Minus 2 times F integral for Q of F U. No, for Dirichlet problem we didn't write M. If U is from H1, 0 of Q, and plus infinity otherwise. Q is bounded Lipschitz, yeah, but it was said many times already, yeah. Q is bounded and Lipschitz. In fact, boundedness is not so important. We can do it even for unbounded Q, but then we should change a bit the topology. Because we will not have, in this topology, in the whole space, we will not have compactness. Why should we introduce another topology? Because in the whole space, the compactness and strong L2 topology, we will not have it. But unbounded domain is okay. And let me continue. Theorem. Let's say 1, 2. The set of function for which U from L2 of Q E epsilon of U less than a constant for any C greater than 0, C less than 0, okay, for any C is R even, because we have this additional term. Yeah, for any C is from R, the set U is L2 of Q is compact. In L2 of Q. Yeah, here for some theta for a positive definite, matrix, constant matrix theta. Yeah, thank you. There is a positive definite matrix theta such that E epsilon converges to E0 and E0 has this form. So it's the statement about the existence of such theta that. Yeah, so far I just formulate that it's. Now look here. This theorem applies because we have gamma convergence and we have compactness. So the solutions of our original problem of Dirichlet problem converge to the solution of the limit problem, which is just PDE problem. And we obtain the results which are already formulated as a consequence of this gamma convergence. Well, similar statement we have in the whole space, but we should do some modification. The topology in this case should be the topology of convergence, which is a weak convergence in the whole space, and simultaneously strong convergence on any compact set. We take the topology of this convergence, and then we can repeat the results here. But here we should add, you remember that in the quadratic form we have extra term with coefficient m. I skip this part because it's clear. Now what I
for almost everything from almost all you have add this works. You had
it's all of course it's almost surely because on the way, yeah, almost surely. Because on the way we will use not Bergov theorem, but subadditive ergodic theorem, and this subadditive ergodic theorem guarantees the convergence only for the set of full measure, what you called omega 0 yesterday. So it's for omega from the set of full measure. Thank you, I forgot to say this. So corollary from these two theorems states that for our original problem, solution U epsilon, solution U epsilon of Dirichlet problem converge in L2 of Q to the solution of the limit Dirichlet problem that reads divergence theta gradient U is equal to F in Q, U belongs H10 of Q. That's just the consequence of these two statements and of this theorem. We have gamma convergence, we have compactness, and we know that the minimizer of this problem is a solution of this equation. So it's really straightforward. This corollary is a straightforward consequence of these three theorems. Well, it remains to understand why we have this convergence. What is theta? Yeah. Now I'm going to explain what our theta is. And that's, in fact, the last thing for which I have time today, but it's a very important fact. And it will explain why we use variational approach here. As I told you, the direct approach is also possible, but it's very technical. And the results which obtained. No, because our operator L epsilon is also negative. Both limit operator and original operator both are negative. So either in both cases we write minus, or in both cases we write plus. Sorry?
In this particular case, we have minus, I guess, because
Theta is positive. Theta is positive.
Yes. Okay, thank you. Otherwise, we have to write plus here. Yeah, sorry. You're right.
The term with them disappears.
No, in Dirichlet problem, we didn't write M. Because Dirichlet problem is already well posed. We have Poincare inequality. M equal to 0, yeah. Well, now, how do we prove this result? Compactness, in fact, I even prepared the proof of compactness. I was going to explain how, but definitely I don't have time. I'm sorry. So it's much more important to explain why we have this, how this matrix theta is defined, and how do we use the subadditive ergodic theorem. So first of all, the subadditive ergodic theorem itself, it's very useful theorem, and I think I should formulate it. So the first subadditive ergodic theorem in one-dimensional case was proved by Kingman, but it was really one-dimensional. So it was for process with just one argument. And clearly here we deal with multidimensional framework, so we need a multidimensional version of subadditive ergodic theorem. And this part is due to Krengel and I don't know how to pronounce this, I think Pike, yeah? And it's 87, it's very old, but all the ergodic theorems were proved in 70s, 80s. And it says the following: assume that we have, okay, we denote by V the R plus to power D, the, not octant, but how do we call it in D-dimensional case? Yeah, I don't know the. Yeah, but D-dimensional octants, I don't know.
Positive sector, positive conus.
Positive cone, it has many different meanings. Well, doesn't matter. New. This is the sets of collection of bounded Borel sets, bounded Borel sets in V, and then we have a functional Fa, the collection of random variables. Each of them corresponds to the set And we assume that the following properties are satisfied. Stationarity. Which means that for any collection F, A1, A2, and so on, it's clear, I think. Its law is invariant with respect to shift, which doesn't send us away from this sector octant, whatever, from V.
He is a subset, right?
Hmm?
Not below. So he is a subset of R plus G, right? Top left, very beginning, up, subset, yeah? Subset looks like belongs. Okay, fine. Yeah, subset.
In V.
Subset.
Yeah, okay. In fact, I thought it's a whole cone, and then we consider collection of bounded Borel sets in.
Лежит, а subset. Является подмножеством.
No, here. Okay.
Вот там, вы, где вы, да.
Sorry. Thank you. It was a misprint, yeah. It just the octant itself, yeah. Then, stationarity should be clear. The law of F(A1), F(A)n is the same as the law of F(A1) plus eta F(A)n plus eta. So if we shift all these sets by the same vector, then the law will be the same. It's the usual definition of stationarity. The only point that the function now is defined on the sets. Statistically homogeneous, yeah. Law or distribution. Second property. It's subadditive. For any disjoint A1 and A2, F A1 A2 is less or equal than F of A1 plus F of A2 if for any disjoint non-intersecting A1 and A2 from this new. And one more condition is a technical condition which is satisfied here. Roughly speaking, this functional for any A, the function of A should be L1 function in omega. It should be integrable. So some integrability condition which are for free in our case, and it should not go to minus infinity too fast. But in our case, functionals are positive. Non-negative, we can even drop this part because the passage to the limit in this part is trivial. So what we're interested in only in the principal part, in the principal integral. So in our case, the function is non-negative, and of course it's bounded by the volume. So with some epsilon, we forget about epsilon. We rescale everything. So in our case, functional is fixed and bounded, so no problem with integrability. So I will not even write down in detail the third condition. Yeah, some integrability. This integrability is really for free in our case. So under these three conditions, we have the following theorem, which is a key instrument in our study. Theorem. Subadditive theorem. Yes, it's often people say Krengel theorem because there are several different subadditive ergodic theorems. For any set whose boundary, not even Lipschitz set, but for set whose boundary, the delta neighborhood of this whose boundary tends delta neighborhood tends volume tends to 0 as delta goes to 0 for any such domain, we have the following convergence. The limit n goes to infinity, n power minus d f of n b for any, okay, b is such that, as I told you, if it's a bounded set which possesses this property that its volume of its delta neighborhood goes to 0 as the neighborhood of the volume of the neighborhood of this boundary goes to 0 as the I don't know. I think there is a name for this type of sets, but I don't know it. For any b with this, let's call it delta property, this minus just multiply this b, it's in the positive segment, so b from
F is energy,
this.
right?
Yes, and f is this f which was there. Maybe it's interact with f epsilon, but it's f which was just defined. Minus volume of b times f bar, the modulo of this guy, tends to 0 as epsilon goes to 0. So for subadditive theorem, there is in ergodic case, there is a constant f bar such that, or if you prefer f bar, no, okay, maybe it's better to write f bar, such that this property is satisfied. It looks like Bergov ergodic theorem, but conditions are slightly different. We assume only inequality.
F are some measures, yeah? You can say that F is a measure of the set.
Well, yeah.
What is
Let me say it accurately. In typical examples, it's a measure, but formally it's just some
a
functional, yeah. Yeah, for instance, it need not be positive. It might be negative, but not too much. In our case, it's not even a measure because in the case of measure, we would have equality here for disjoint sets.
Stationarity law, if you have when describing FA, you describe FA and write okay because the sets are random.
Yeah.
In the sense of class 1, in the case of class 1, right? It's also
No, okay. There is no contradiction here. It's the law, but it's not an additive functional. It's really subadditive functional. If we take two sets, that for the union, the functional might be smaller. And in our case, it will be exactly the case.
When you say this property of stationarity, what does it mean? Law of FA1, FA2?
If we consider two sets here, and then we shift them, both of them, then the functional for this pair is the same as the functional of this pair. But it doesn't mean that the functional of this pair is the sum of functional of here. It's only invariant with respect to the shift for the whole collection.
There is no probability, actually.
No probability.
No probability.
No, it's okay. Probability is here. There is argument omega, and everything is the law. I don't say that it's equal. The law of this will be the same as the law of this.
This function will depend also on some omega.
Omega, yeah. And for each omega, they are in this.
They have these properties.
Yeah.
What is epsilon in your theorem? Below.
Epsilon?
Yeah, in the theory which you presented.
Лим,
Sorry. It's already written. Is equal to 0. Yeah, sorry. It's nothing. Well, now let me explain you very briefly what difficulty we faced. Our function is non-local.
Very general statement.
Yeah, it's a very general statement. Our functional is non-local, so we would like to say that our set is just energy, which is concentrated in our set when both x and y are in the set. And in this way, as usually in gamma convergence, we consider the growing cube divided by the energy in the growing cube, pass to the limit, and use this subadditive theorem to justify that exists a limit. And this limit gives us this matrix Q. But it's just existence theorem, would be existence theorem. But since functional is non-local, when this set are very close to each other, they start to interact. And this way we lose this property immediately. Because this mutual interaction between two closely located set destroys the subadditive property. What do we do? Just last couple of minutes. Do I have a couple of minutes? We do the following. We take our functional and we say that's our set B, in which we set A, in which we want to define our functional, and we do the following. We first assume that our A has a finite support. First case. Then we show how to reduce this general case to this one. A has a finite support. And let's denote the radius of the ball in which to which the support belongs by R. That's R, and that is the support of A. Then we do the following. We make consider the R neighborhood of the boundary of A. And in this part, we say that test function should be equal to some eta times x, just linear function in this R neighborhood of dA. And when we take the minimum, we admit the we vary function u only in this smaller set. With this trick, the functional is getting subadditive, because as long as this value is prescribed, we can show that if two sets are very close to each other, on this side we'll have the same linear function, and this match, these two different functional defined on two different sets, and we obtain that the function we define this way is subadditive, and all this technique works. Eta, we want to define the eta, because in the limit functional we have this form. As usually in gamma convergence, we, in our compactness theorem, the second part of our compactness theorem is not only the set of with bounded energy is compact, but any limit point is an element of H1. For the case of H1, we can approximate it in this norm by piecewise linear function. So as usually, it's the usual trick in gamma convergence, it's sufficient to define the gamma limit only on linear functions. Then we take this particular linear function and use subadditive theorem to construct this expression. On the way, we face this essential difficulty. But then when we enlarge the size of the cube, clearly the influence of the layer along the boundary that doesn't play any role in the limit. So the limit with restriction and without restriction will be the same. Then we obtain the formula for theta, which is just defined by as subadditive limit of the energy defined on set A, on growing set A, with this additional condition.
What is additional condition?
Function u, test function, let me write it down then. F eta of our set A, we wrote like this, Fa eta is equal to minimum of integral over A, integral over A of x minus y, mu xy, u of x minus u of y square dx dy over the set u is equal to x times eta in R0 neighborhood of dA. So we impose additional condition. A, not arbitrary function from L2, but A should be equal to this particular function in the whole neighborhood of. If we have to, in the case of differential equation, we would impose this condition only along the boundary. But here we will lose subadditivity. So we impose in the layer, which depends on the support of A. And this gives us the desired subadditive theorem, that gives us desired existence of the limit. For compactly supported. Otherwise, we do the following. We take arbitrary A, we cut, we approximate, we just cut, and we show that the cutted sequence converge to the limit in with respect to the cutting parameter. And this limit, it's just technical thing to show that this limit converges to the true gamma convergence result.